Hello learners, welcome to yet another practical physics class. In this class today, we are going to demonstrate an experiment to verify Archimedes Principle. My name is Vyekwaso Semakula Samuel. I am a physics teacher. Archimedes' principle states that when a body is partially or wholly immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. So in this experiment, we are going to use this stone as our body. We are going to get it immersed in water, and we want to see if the weight of the water displaced is equal to the upthrust which is exerted on this stone. So like we said, we are going to use this stone as our specimen object. We are going to have an overflow can so that we can collect the water that will be displaced when this stone is fully immersed. Then we shall use our spring balance to measure the weight of the water displaced, and then we shall get the weight of the stone in air. Then we shall get the weight of this stone when it is fully immersed in water. The weight in air is called the real weight. The weight when it is fully immersed in water is called the apparent weight. Now the difference between those two is the upthrust. So we are going to get the upthrust, and then we shall determine the weight of the water displaced, and if they are equal, then we shall have verified Archimedes' principle. We shall begin by determining the weight of this empty beaker. This is the beaker that we shall be using to collect the water displaced by our stone. So the weight of this empty beaker is 1 Newton. It is here 1.00 newtons. So we record the weight of the empty beaker as 1.00 newtons. Next, we shall get the weight of this stone in air, which we said is called the real weight of the stone. So the real weight of this stone is 0.25 newtons. So the real weight of the object is 0.25 newtons. We record that in our data. Next, we'll need to find the weight of the stone when it is fully immersed in water. At the same time, we shall collect the water that will have been displaced by the stone. So we shall use the overflow can. We shall fill this overflow can with water. Then we shall suspend the stone on the spring balance and lower it until it is fully immersed. We shall collect the water in this empty beaker, and thereafter we shall find its weight, but we shall also take a reading to give us the weight of this stone when it is fully immersed in water. So we have filled the Eureka can, the overflow can, with water just up to the spout where the water goes out. Now we are going to suspend the stone and then lower the stone into the water and then collect the water which will have been displaced. So there we go. We have the stone freely suspended and fully immersed in the water in the Eureka can. The water displaced is being collected. While that is happening, we'll need to take the reading. What is the weight of the stone recorded now? It is now 0.15. Record the apparent weight of the object, which is 0.15 newtons. Now, the upthrust is the difference between the real weight and the apparent weight. So the upthrust will be 0.25 minus 0.15, and this gives us 0.10 newtons. We next determine the weight of the beaker plus the water displaced. The weight of the beaker plus the water displaced. And this is 1.10 Newton. The weight of the beaker with the displaced water, which is 1.10 newtons. Therefore, the weight of the water displaced will be 1.10 minus 1.00, and that gives us 0.10 newtons. So we have the weight of the water displaced, and right here we have the upthrust. From these readings, we realize that the weight of the water displaced is equal to the upthrust, which is what Archimedes' principle talks about.